Hey guys, this is chapter 32, Magnetism. So in this part of the lesson, we're going to refresh your understanding of magnetism, and we're going to talk about some basic concepts that you can use in problem solving. If you go to my classroom, there's a box that says Magnetism Unit, and inside you'll find some materials that you can work with. But please just make sure that you put the materials back so that the other classes can use them. So I want you to do some observations with a single bar magnet, and there is a horseshoe magnet. If you look in the cabinet, that's the first. It's the if you're looking at my classroom, it's the first lap table on the left-hand side, and it's the cabinet behind, just behind that table. If you look in there, you should be able to find a horseshoe magnet if you want to look at one of those two. And you're going to look at the magnetic fields with the iron filing transparency sheets. So go ahead and discover what those fields look like. Okay, before we get started on lecture, I just want to mention that I am losing my breath quite often, so please ignore that. All right, so let's talk about magnetism. Magnetic fields are measured in Tesla, and Tesla is represented by a capital letter B. In Regents physics, we did not calculate anything with Tesla, but we did mention that the magnetic field was represented by a B. It is a vector quantity, and we know the polarity of a magnet by using a compass needle, and the compass needle is points north. So we can determine the polarity of a magnet by using a compass. A compass is a little tiny magnet. Magnetic forces are long range, unlike electrostatic forces, which are short range. They do have dipoles. Obviously, there's a north and a south pole. However, one of the differences between magnetism and electricity is that with magnets, there's no isolated north and south pole. They come in pairs. So you get a north and a south in a pair. You can't have just a north magnet and just a south magnet like you can with a negative charge, obviously, and a positive charge. So we can't isolate those north and south poles. Field lines are drawn from north to south, so out of north and into south, and that's synonymous with a positive for north and a negative for south if you think about the field lines that we drew in electricity. The magnetic fields never end. They are continuous, and they even go through the material itself. So there are similarities between electric fields and magnetic fields, but they're not exactly the same. Anything that's attracted to magnets are called magnetic materials, but not everything is magnetic material. So not all metals are necessarily magnetic. And the magnetic materials, they don't have poles. They're not magnets themselves. So they're kind of analogous to neutrals, whereas we have in electricity, positive and negative both attract to neutrals. Our north and our south pole both attract to any part of this magnetic material. However, the difference is that not every metal is a magnetic material. So a good example of magnetic material is iron. So do magnetic field lines ever cross each other? And you should know the answer to that. So some really cool stuff. There are many different organisms that have magnetic material within them, within their bodies, that act as a compass to tell them how to navigate through their world. And I think that's pretty cool. It's not just, a select few. There's many different organisms that use this type of principle in order to navigate and find food, basically. One is this bacteria spirillum, and has this magnetic material that acts as a little tiny compass inside their bodies. Tells them where to go. Very interesting. Also, some birds have this type of property as well. I'm not exactly sure biologically how that works, but the same kind of idea in navigation. So, how was magnetism has been long discovered. We understood that magnets existed long time ago. However, it was in 1819 that Hans Christian Ørsted was doing a demonstration in his classroom, and he was just in a lecture. He had always been interested in the idea of connecting or finding some sort of connection between electricity and magnetism. But he wasn't really trying to do that in this lab demonstration. He was just trying to just show a simple circuit. He happened to have a compass needle nearby, and when he turned the circuit on, he noticed that the compass needle changed direction. And so he discovered this connection between electricity and magnetism. It was further developed by Ampere, and we'll talk about that in the next few slides. So we really don't know. When a magnet is broken in half, we still get a new north pole or south pole, well, both, when the magnet is chopped in half. So we don't have any kind of what are called monopoles. Those, singular north or singular south poles. It always comes in pairs. So we're not really sure how that works, and that's really like a cool kind of thing that you obviously don't get with electricity. So if you take a north-south magnet and you were to chop it in half, in the middle there, you would get a new north and south pole. That's pretty cool. So our Earth is like a giant bar magnet. Again, another concept that you learned in Regents physics. We think that the convection currents within the core of the Earth, those currents have caused a magnetic field or cause a magnetic field. And so really, it's not really like a permanent magnet. It's more like an electromagnet inside our Earth's core. But they use a bar magnet to show how the field looks around our Earth. Our geographic north is actually the magnetic south of our Earth. And that's why with our compass needles, they point north because they're attracted to the south magnetic pole. There is a pole axis. The axis is not quite aligned with the tilt of the Earth. However, you might think that it would be. It is slightly off, and it is changing. And so what that means is that these poles have reversed some time ago, and they continue to do so. It takes a really long time to reverse itself. It's not like when the poles reverse that everything kind of flies off the Earth. Obviously, we know that gravity would still exist. So it's kind of silly. People come up with some silly concepts there. So the study of how the Earth is affected by this magnetism is called paleomagnetism. So if you're interested, you should definitely check that out more. Let's see if we can see this little cartoon. Probably not. I think maybe I'll try to get that for you a little bit better. But I think the idea is the paramecium are floating all around because the magnetic field reversed or something like that. So anyway, I will try to get that a little bit better for you. So what Ørsted discovered was that this current carrying wire created a magnetic field in which the compass needles responded to. And so we have a diagram here of a current carrying wire, and at first there's no current in the wire, so we're looking here at this diagram, and we see that the compass needles are all facing to geographic north. And once the current is in the wire, once the current is allowed to flow, and we've allowed the current to flow upward through this wire, what was noticed by Ørsted was that these compass needles aligned themselves in a particular fashion. If you notice the direction of the red, which is north, the direction of north goes around the current carrying wire in a counterclockwise fashion. So this was always true. And if the current was reversed, and if the current went this way, then the compass needles went the opposite way and they went clockwise. So Ørsted developed what was called the right-hand rule to help determine the direction of the currents and the magnetic fields according to one another. So let's take a look at that. So if we have the current going up the wire, so we have current flowing up, we're going to let our thumb be the direction of the current. And we're going to literally grab the wire and put our thumb in the direction of the current. The direction of the magnetic field is how our fingers curl around the wire. So if you grab the wire, your fingers are curling counterclockwise. And so that would be the direction of the magnetic field, would be counterclockwise around the wire. If you take the current and flip the direction, let's make the current go down instead of up. That means that when we grab the wire, our thumb points down, and notice that the direction of your fingers will curl clockwise instead of counterclockwise for that direction. Okay, so that's the right hand rule. We're going to use our right hand quite a bit in order to determine directions, especially when we start talking about the 3 dimensions of force and current and magnetic field. And velocity, actually, for that matter. Some symbols that we did not use all the time in Regents physics, but we will use all the time in SUPA, is the direction of the field into and out of the page. So sometimes the field obviously is drawn like, on the page, moving left or right or up or down. But some of the time we're going to have our magnetic fields going into and out of the page. So if you think about an arrow, if you're looking at the tip of the arrow, you're looking at the point. And the point is coming out of the page towards your face. And that's why you see the little dot. If you look at the butt end of the arrow, I said butt, and that means that the arrow is going into the page, that's the direction of the field. So you'd be looking at the tail of the arrow, which looks like an X. Well, we know that real arrows have 3 fins on it, or feathers on it, but they have 4. Anyway. So those are the symbols that we use for into and out of the page, because we're going to be working in 3 dimensions. Magnetic field is created all through space surrounding a current carrying wire. And we know that it's a vector quantity, and it is represented by a capital letter B. The magnetic field exerts forces on other magnetic poles like compass needles. And the force that's acting on those poles is parallel to or in the direction of the magnetic field. It is aligned with the force that's acting on the North Pole is aligned in the same direction, or 0 degrees, with respect to the magnetic field. And the force exerted on the South Pole is 180 degrees with respect to the magnetic field. So what happens is, since there's these forces acting on the poles of this magnet or compass needle, it creates torque. It creates spin on this compass needle. The compass needle will align itself with the magnetic field. And you saw this in Ampere's law. The magnetic field circulating a current carrying wire allowed for the compass needles to magnetically align themselves with the magnetic field, showing the magnetic field. So this is the reason why we can use compass needles to show the direction of the magnetic field because of this torque that's created. So there are forces that are exerted on magnetic poles that are present in another magnetic field. Like I said, the magnetic field is a vector quantity, and when we're talking about the circular magnetic field that exists around a current carrying wire, that magnetic field is going to always be tangent to those magnetic field lines. And obviously we also know the concept, or understand the concept, that the closer you are to the current carrying wire, this magnetic field strength would increase. So that's still true. And the farther away you are, obviously that magnetic field strength decreases. You should understand that there are two different types of magnetism, one caused by magnetic materials or permanent magnets, and like a bar magnet or magnetite. Those are permanent, or neodymium. Those are all different types of permanent magnets. But we also have magnets that are caused, magnetism that's caused by moving charges. So like referring to Ampere's law. So one other thing to mention is that we know that all charges have electric fields, but it's only moving charges that create electric and magnetic fields. So that's really important. The charges must be moving in order to create the magnetic field. That's why you can have the circuit hooked up but not turned on, and you won't see that magnetic field created with some compass needles. As soon as you turn the current on, that's when the magnetic field is created. Alright, so let's stop to think about this. We have a current carrying wire. It shows the direction of the current, and then they show you a point P. What do you think is the direction of the magnetic field at point P? Up, down, into the page, or out of the page? So we know that the source of a magnetic field is a moving charge. So how are this moving charge and the direction of the magnetic field related? Well, we've used the right-hand rule to show the magnetic field around a current carrying wire. But what if these charges were moving within an electric field, and the electric field were we were looking more like into the wire itself or into the material itself? We want a more three-dimensional view of what's happening. So we know that the moving electric charge creates the magnetic field, but in what direction in respect to one another? So we have a charge here, it's a positive charge, and we can see that the positive charge is moving in this direction. Let me get red here. Into this direction, which is the negative y direction. And so we also see that the magnetic field, as a result, is set up. Let's see, if I put my thumb and I grab that wire, the magnetic field would be following my fingertips. We're going to use a different right-hand rule, but just for now, using our first right-hand rule, if I grab, let's say that's a wire in this case, my fingertips would be pointing towards the positive x direction, which you can see in green here. If this were current carrying wire, I'm not saying that it is, but the same principle should be applied. So you can see that 90-degree or tangent to the wire at that point, which we'll call P. Okay, we'll call that point P. Now the distance with respect to where the charge is and the magnetic field in which we're trying to calculate, we call that vector r. So that's a distance vector. And we know that as the distance increases, that magnetic field will decrease. We haven't looked at the relationship mathematically, but we do know that concept. The Biot-Savart rule gives us this relationship between magnetic field and distance with respect to the velocity of the particle and the charge of the particle. So there's a few terms here that are new to us. We know that the direction is determined by the right-hand rule. You're going to learn a slightly different right-hand rule in a second. The angle theta is the angle between the velocity vector and the distance vector. So that angle theta would be here. Okay? And you can see that's in the YZ plane. And the V in this formula is referring to the V in this formula is referring to the speed of the particle. Q is obviously the charge of the particle, and R is the distance, the position between the particle itself and where we're trying to find the magnetic field. And so then we have some constants out front. The constants out front, this mu naught is the permeability constant. And it's not too far different of a concept in terms of like the permittivity of free space that we used in the electric fields equation, the E naught. So it's not too different of an idea than that. So we have the permeability constant, which is 4 pi times 10 to the negative 7 Tesla meters over amps, or that is equivalent to 1.257 times 10 to the negative 6 Tesla meters over amps. So I'd make sure that you have that down. We can use this equation to show the relationship between that field strength and the distance. So you can see that there's an inverse relationship between the field strength and the distance. So that's very similar to the electric field strength equation, that we have this inverse square law. So it's like Coulomb's law, but it's dependent on the angle between the velocity and the distance vector. So we have this theta dependency, unlike what we had in Coulomb's law. So that's basically the only difference, but you still have that inverse squared law relationship. So one more thing, 1 Tesla, or 1 T, which is the unit for the magnetic field, is equal to 1 Newton over amp times meter. Okay? So we have 1 Newton over amp times meter is equivalent to Tesla. So in this example problem, we're going to look at the magnetic field around a moving proton. And this is very similar to the diagram that we use to describe the Biot-Savart law. So we have a proton that's moving in the direction of negative x, and we want to determine the magnetic field at some different locations here. We're going to find the magnetic field at P2, P3, and P1. So I'm only really concerned right now with the magnitude of the magnetic field and not necessarily the direction. I'm going to talk to you about direction in the next slide. So we just learned the Biot-Savart law, which we have the equation for here. And we have the positions that I would like you to find the magnetic field for. I've given you the velocity of the proton, and so we have V. We know the charge of a proton. I've given you the constant, the permittivity constant, and we obviously know 4 pi. The angle theta you would have to determine using trigonometry. So you would have to determine what theta is here. That is the angle between your position vector. In the case of P3, this is your position vector R. In the case of P2, this is your position vector r. In the case of P1, your position vector is aligned with V. So you want the angle between V and R, so that would be different. That angle would be different in each of the cases, P1, P2, and P3. Also, your distance would be different for, well, at least P3. P1 and P2 have, they are equivalent in their distances, just different directions. So go ahead and determine the magnetic field at each of those positions, and let's see what you find. So at position 1, you should have found that because the angle between V and R at position 1 is 0 degrees, sine of 0 would have yielded 0, and therefore we would get our answer for the magnetic field to be 0 Tesla at that point 1. At point 2, using 90 degrees between V and R and a distance of 1 millimeter, if you've used your equation and done your math correctly, you should get 1.6 times 10 to the negative 13 Tesla. And I'll talk about the direction in the next few slides. And then at 45 degrees, and the distance of 1 radical 2, you should have gotten 0.57 times 10 to the negative 13 Tesla. So obviously you can put that in correct scientific notation, but I wanted to show you with respect to one another in the same magnitude or power of 10, how they compare. So obviously the magnetic field when it's at point 2 is greater than it would be at point 3, and mainly the reason is because of the distance. So you have it's farther away, and so you have that inverse squared relationship shown here. Since the magnetic field is a vector quantity, we need to use the principle of superposition in order to add the magnetic fields due to various moving charges at different locations. What I mean by that is if we obviously have more than one charge moving in a wire. So if we have multiple charges at multiple locations along that wire, obviously throughout that wire, then all of their magnetic fields are going to add together vectorially. So we go back to that long, like, x plus y plus z, and then the Pythagorean theorem and blah, blah, blah. So that's a lot of work. And remember, we can use a cross product to simplify our lives, which is beautiful. So when we're using the cross product, or V cross, I think we're going to do V cross R, then it makes things a little bit easier in terms of determining those magnetic fields as a result of multiple charges. So we're going to use that instead. So in this example, I'm going to show you another right-hand rule, and we're going to put our fingers in the direction of the first vector in our dot product, our cross product rather, is V. So we're going to put our fingers in the direction of V, and then we're going to curl our fingers or bend our fingers towards our next vector quantity, which is R. So V cross R. So we take our fingers, point them in the direction of V, bend them towards R. What is the direction that your thumb is pointing in? Your thumb should be pointing into the page or into the screen. So that is the direction of the magnetic field at that point. So V cross R, your fingers in the direction of V, bend towards your cross product, your next vector R, and your third vector is your thumb, and that's going to give you the direction of the magnetic field. So that would be into the page for this example. All right, so at this point, I'm going to break the lesson, and I'll give you guys a little bit of a break. We could work on some of your your task ranking and your conceptual development at this point. We're going to get into a little bit more complicated moving charges and current through a wire and how that affects the magnetic field in the next section of this lesson. So for right now, hopefully you've learned the basics. Also, because I'm not there, another good idea, and you should have been doing this all year long, but a great idea is really to read the chapter. This is a very, very big chapter. It will take us quite a bit of time to get through. So make sure that you're following along and really understanding what's going on before you move on. So in the first lesson, we talked about different properties of magnetism and how current carrying wire can produce a magnetic field, and some of the ideas related to that in terms of direction of the magnetic field using right-hand rule. And we also talked about how a moving charge, the direction of the velocity in relationship to the position of where we would want to determine the magnetic field, that we use a cross product there to determine the direction of the magnetic field at that point as well, using a slightly different right-hand rule. And so in this lesson, we're mainly going to focus on the magnetic force of a current carrying wire. And in order to do that, we want to use the Biot-Savart law that we learned, and we want to place it in terms of I instead of the charge's velocity. We want to look at this in terms of the current, so all of the charge moving in the wire. And this does require some calculus, so bear with me. You can see in purple the derivation and how we get I into this formula. In the first Biot-Savart law, we used the charge Q, a singular charge Q, little q, times the velocity V. So in this current carrying wire, we have many charges. So if we look at a section of the wire, follow me down to this diagram here. If we look at this section of the wire, then there's a quantity of charge within that wire that's moving. So we have a change in charge Q and times the velocity V. If we look at this this section of the Biot-Savart formula, let me just underline it for you. If we look at just this section, we can derive a new equation. We can substitute in our current because velocity can be calculated as the change in position over time. And so if we use change in position over time for velocity, then you can use Q over T, and instead Q over T, replace that with I and leave your change in position. So now, instead of using the change in charge or the quantity of charge times the velocity, QV, we can use I change in S. So that's where we've replaced it here in the formula. Okay. Notice that this formula is showing that the position vector cross the change in distance vector. So in other words, we have, let me highlight it here for you, talking about this section here. This is a cross product, but it's a cross product between the direction only of R, so not the quantity. That might be something new that you're not used to. If you look, it's the R hat, it's the R direction. So in other words, when we normally do a cross product, we have change in S, cross R, you know, it would be times R, and then sine alpha. Okay, that's normally what we would use for a cross product. But since this is just indicating direction, we're not doing cross product of the two magnitudes. We're doing cross product of the direction between the magnitude of change in S and the direction R only. So we're not going to end up with the magnitude of the position vector on top of this equation. So that's really important that you understand that. Using a bit of calculus, if we integrate this function for the entire length of the wire, we're going to yield this equation. And you can look at, there's an example, I believe it's 32.4, nope, just kidding, 32.3. You can look at the derivation using the integration of this equation to derive this new equation here that's much more simplified, okay? So D in this equation is referring to the distance away from the line, or distance away from the current carrying wire. So that would be this distance here away from the current carrying wire, okay? That would be D. Calculus students, you definitely need to take a look at this, and I will show you my work in the next slide. All right, calc people, so if we take a look at this same diagram, if we look at a section, change in X here, we have, I'm not going to go through all this, you can take the time to do that yourself and look at the example problem in the book. But if we look at this change in X here, we know that there's quantity of charge within that segment, and we're looking at this point P away from the segment. So we want to be able to look at all of the segments. So we want to integrate this entire wire so that we're including every part of the wire to allow for the total magnitude of the magnetic field at this point P. So in order to do that, we need to integrate. So we have the function here. I said I wasn't going to go through it all, but now I am. So you have the function there. We want to integrate that. Remember that this is r hat. This is just the direction, not the magnitude. So we're just looking at the direction between them. Magnitude of the direction is a 1, so we tend to ignore it. I really didn't mention that in the last slide. So anyway, all of this is on, I guess, on page 927, but again, you want to look at example 32.3. So if we start to look at that in terms of instead X and D, remember when we want to integrate, we want to get all of our dimensions consistent with one another so that when we integrate it's a little bit easier. So that's what they do at first in this example problem. They get R in terms of X and D, which is the distance away from the line or from the wire. Keep on calling it a line. And then they also put the angle in terms of the quantity or the dimensions for meters. Also, we've done that before. And then they go ahead and integrate the function. So obviously, they don't even show the whole integration. So once we integrate this function here, once we integrate this, they use Appendix A. You can see that using Appendix A in the back of your book, you get this equation. We want to evaluate that from negative infinity to infinity because this is an infinitely long wire. And as a result, we get this equation. So I guess that didn't take as long as I thought it would. But the direction of that magnetic field is tangent to the circle that's around that current carrying wire, and you can use the first right-hand rule that we talked about with Ampere's law. All right, so this is a couple step problem, but I think that you can handle it on your own. This is to determine the magnetic field around a heater wire. And the heating wire is 1 meter long. It has a 1 millimeter diameter. It's comprised of nichrome, which the resistivity of nichrome is 1.5 times 10 to the negative 6 ohms times meters. It's attached to a 12-volt power supply. And so we want to know what is the magnetic field 1 centimeter away from this wire. So you're going to use your new derived formula, mu naught I over 2 pi d. Now, you can determine that we don't have the current, but we do have enough information to determine the current in a couple of steps. So I'm going to let you try to work out finding the current and then using the current in this equation to find the magnetic field. I also would like to know by the right-hand rule what the direction is of this current. So To begin with, you need to find the current. And in order to find the current, we can use the equation potential difference over resistance. The problem is we don't have the resistance. We do have the power supply of 12 volts. R, the resistance of this wire, is dependent on the resistivity of the material. So we have rho L over A. And that information we do have. We have the length of the wire 1 meter, and we can determine the cross-sectional area because we have the 1 millimeter diameter. So I'm not going to show you all the plugging and chugging, but for the resistance, you should have gotten 1.91 ohms, or about that. And then if we plug that in for the current, you should have gotten a current of 6.28 amps. Then, using that current, we can plug that in. We have the mu naught, permittivity. We have 2 pi, and we have the distance away at 1 centimeter. Make sure that you're all dimensionally consistent, and you should get the magnetic field to be equal to 1.3, or about this, 1.3 times 10 to the negative 4 Tesla. So what is the direction of this magnetic field? If we allow the current to go, let me move this if I can. If we allow the current to move to the right as I've shown in the diagram, we place our thumb in the direction of the current, grab the wire. The magnetic field at a point 1 centimeter away would be going into the page. Let me draw that correctly. Into the page on the bottom there, and then we'd be coming out of the page using correct notation, out of the page at the top position 1 centimeter away. So hopefully you got that right and you had no issues solving. So you should recall finding the electric field about a ring, and we had like quite a complicated formula that we used calculus to derive. And if you remember, it was very similar to like 1 over z squared plus r squared to the 3/2 power or something like that. So we're going to see a similar equation here for the current about a loop, and sorry, the magnetic field about a current carrying loop. We want to get a single loop so that we can take a look at multiple loops. We just would multiply it to magnify the field strength. So we show the derivation for this using the calculus, using similar methods to what we did with the electric field. They show this on page 930. So you should take a look at that derivation. Calc people definitely do that. And you'll see the similarities between the electric field strength and how it was calculated, and how this magnetic field strength is also calculated. So eventually they arrive at the formula for this loop, magnetic field about a loop. And we're at point P at some position Z away from the loop, from the center of the loop. And the R vector you can see, let me make this bigger actually again. The R vector you can see is coming from some segment of the loop out to that point P. And we want to integrate that for the entire loop. And we can also see the angle gamma, which they have in between R and the z-axis. And then they have the direction of the segment change in S, which would be tangent to that segment. And then they also have the current direction as well. Okay. The magnetic field at that position is the sum of, at every position around the loop, we can see that the I, in other words, X and J, Y, components of the magnetic fields cancel. And so we're really looking at the sum of the Z components of the magnetic field due to each segment as we go around this loop. Please make sure you look at the example problem 32-5 on page 930 and look at how this equation is derived. So they do finally arrive at this top equation here, and it does look very similar to the electric field equation for a loop in terms of the dimensions. And if we wanted to look at multiple loops, we would just multiply the number of turns. So it's just a matter of magnifying the field for every single loop. It's just a multiplier, and we add in that capital letter N, which is the number of turns. So every turn or every loop is going to multiply the magnetic field by that factor. This example problem is called matching the Earth's magnetic field. So we want to know what current is needed in a 5-turn, 10-centimeter diameter coil to cancel the Earth's magnetic field at the center of the coil. So what we want to do is we want to look at this magnetic field of the Earth, which is 5 times 10 to the negative 5 Tesla, and we want to match that. So we're going to use that as the magnetic field of this 5-turn loop. We have the number of turns, which is 5. We have the radius, which I gave you. The radius is going to be 10 centimeters divided by 2, because that's the diameter, 10 centimeters. And then all we should have to do is solve for the current I. So go ahead and do that, and let's see what you get. Okay, so once you plug in your information, you should have gotten 0.8 amps in order to match the magnetic field of the Earth. So if the current, if you take your right hand and you put your thumb in the direction of the current and grab the wire, you should see that the field is going to be towards the top. So it's going to go through the loop and up through the loops. Very similar to what I just did in the example problem. If we grab the loop, if we put our thumb in the direction of the current and we grab the loop, you can see that your fingers will curl in. And so the magnetic field is going to be directed through the center of those loops from right to left in this case. So that's how we can use our right hand rule to determine the direction of the magnetic field in these current carrying loops. Notice the concentration of the field. The concentration of the magnetic field is very, very large or intense inside the loops, but really non-existent in the outside. So we have what's called like that fringe field, very, very weak magnetic field outside the loops, so pretty much no field outside the loops, and that strong magnetic field inside the loops. By creating these loops, this number of loops, we're creating what's called a magnetic dipole, because in essence, we are creating this magnetic field which is directed from north to south. So really what we end up with is we end up with a north side on this side and a south side on this side. So we're creating a dipole by running current through these loops. If we slice this down the center and we look at a cross section, we turn it and look at the cross section, the view would look like this. So we have our current running in the loop, and remember that the point, actually we'd be looking at from the south side, we'd see the points or the magnetic field coming towards us in the center, and the magnetic field going away from us on the outside. Okay, so just around that loop, if you take your thumb, grab the wire or grab the loop, put your thumb in the direction of the current, we go into the page on the outside, and then we're coming out of the page through the center. And so again, we'd be looking from the south side of this solenoid. That's what loops, the loops of wire together called a solenoid or electromagnet. So as I was saying in the last slide, we have this loop. You can grab the loop with your right hand, put your thumb in the direction of the current. You can see that the field is going to go through from left to right in this case. Remember that the magnetic field runs from north to south, meaning out of north and into south. So in the case of this loop, we have the north side of the loop as this side here, the north side, because the field lines you can see are coming out of the north, and if we were to follow this field around, we would see it would go into the south. So this is the south side here, which means that the polarity of this loop is north on the right and south on the left. And if you have a bar magnet, as shown here, and we have the north side of this bar magnet nearer to the north side of this loop, we can see that they would repel, hence the direction of the force in red, showing that this loop would be forced away as we bring this bar magnet closer to the loop. So hopefully you can see that pretty easily. And again, down here I'm just saying that remember that the North Pole is the end that the field is emerging, and the south side is where the field is going in. So north is emerging field, and south is where the field is going in to the loop. So literally, if I were to hang this loop from a string from the top of a ceiling or something like that, and then I bring this magnet, this permanent magnet, near to the loop as I'm running current through the loop, we should see the loop being forced away. So if you recall, the electric field of a dipole was given by the equation 1 over 4 pi epsilon 2 of the dipole moment over z cubed, which was the distance from the dipole, and on the z-axis, whereas the dipole was sitting on the xy plane. So we simplified that equation because we allowed the distance from the dipole to be much, much greater than the actual radius of the dipole itself. And so when we do that, we can simplify the equation. We're going to do the same thing for the magnetic field. So you can see the equation. We've already had this equation. But if we let z be much, much bigger than r, then we can allow z to go to z cubed. And so our formula now becomes here for the magnetic field about a loop. Okay, so we can change this equation a little bit. If we substitute in 2 pi on top and 2 pi on bottom with a coefficient of 1 there, then we can see that the 2 pi on the bottom becomes 4 pi, and on top we get 2 pi r squared I, but 2 pi r squared, or pi r squared, is just the area. So we could put this in terms of area instead of radius. In that previous equation, AI represents the magnetic dipole moment, which we call mu. And I know this is really annoying because mu and mu naught are not the same thing. Mu naught being the permittivity, and the mu with a bar over it, or vector over it, is the magnetic dipole moment. So, you know how they do this. They like to use the same letters for everything. Unfortunately, that's what it is. And when we're looking at this dipole moment, the magnetic field is on the same axis as the dipole moment. So because the dipole moment and the magnetic field have the same direction, you can use the right-hand rule in order to determine the direction of the dipole moment also. Alright, so I want you to stop and think about this. What is the polarity of the field, and what is the direction of the current around this loop? So you should be able to answer that based on what we've talked about so far. So hopefully you said that the north is through the top because it's out of north and into south, so the south would be on the bottom. And the direction of the current would be counterclockwise by the right-hand rule. Alright, so this is the end of part 2. We're a little less than halfway through this chapter. And before we start getting into something called line integrals, I'm going to break the lesson here.